आपका वॉइस म्यूट है, माइक म्यूट है, सॉरी।
Okay, friends. Good morning to everybody. This is Pune Hams Sunday Tech Talk. Sorry for the delay. Sooraj is going to present a workshop on antenna tuners. So without spending much time, I already shared all the details with you. I will request Sooraj to start the presentation. Over to Sooraj.
Okay, thank you once again, Pune Hams and Tech Forum for giving this opportunity. And good morning, all. Thank you for joining this workshop session. My handle is Sooraj. Most of you already know me. My call sign is VU3ZAG. And today I'll be taking this workshop session on antenna tuners. So I would like to have this session as a interactive session. So I would request all to keep asking queries or correct me in case I'm presenting something wrong as well throughout the session. So thank you once again. So first of all, I will start with some basic terminologies related to antenna theory and waveguides, and some terminologies that are important and I will be discussing throughout this workshop session. So first of all, we will be discussing these terminologies, and then we'll be discussing about the requirement of an antenna tuner. And finally, we'll be discussing about how to build one QRP tuner with some of the passive components. So, starting with the basic fundamental terminologies related to antenna theory. So, the most important thing that we usually hear when we talk about RF and radio frequencies and impedance. So the first question is that, so what's the impedance? So we know that the main passive components, that is resistor, inductor, and capacitance. So these are the main elements that are used in almost all the electronic components, all the electronic devices. So these are the components that are also used in RF frequencies also. So impedance is nothing but the effective resistance, which includes resistance of a basic resistor and as well as the reactance offered by inductance and capacitance elements in a particular AC circuit. So the impedance is only applicable when the frequency factor comes into picture. So for DC, the impedance value will be purely resistive. So, but first of all, what is reactance? So as I mentioned, it is a combined resistive effect which includes resistance as well as reactance. So what is reactance? So reactance is nothing but the opposition generated by inductance as well as capacitance for the flow of AC currents through it. So again, the term comes only in the picture when an AC signal, that is the signal which is having a frequency factor, comes into picture. So okay, so these are the two graphs that represents the reactance. The first one is for inductive reactance. As you can see, the formula for inductive reactance is XL equal to 2 pi FL, where F removes the frequency and L is the value of the inductance. So it is directly proportional to the frequency. So when the frequency increases, the reactance produced by the particular inductor also increases. Okay. The second one is the capacitive reactance. Capacitive reactance is the reactance offered by the capacitor for the flow of AC through it. So here the formula is 1 by 2 pi Fc. Okay. So F is in denominator. That means it's inversely proportional to the frequency. When the frequency increases, the reactance offered by the capacitor decreases. So it is a this type of curve. Now the next important part is resonance. We know this model, that is girl swinging on this type of hula. So you know that there's some natural frequency and the fundamental frequency. So the resonance happens in the same condition. This is actually a physical type of explanation. When coming into radio frequency, we can explain that the resonance frequency occurs uh, at the point when the capacitive reactance and the inductive reactance cancel each other. So actually, the point of resonance, the capacitance and inductive reactance will be equal and opposite. So they get cancelled to each other. And at that point, the only available impedance will be the resistive. Okay. So we can represent as Z antenna, the combination of resistive impedance plus J. J will be the reactance, either capacitive or inductive. So when impedance occurs, this factor cancels out and the only left will be resistive. Okay. So why matching or tuning is important? So this is a diagram shown here is a simple network in which the source impedance is set 0. Okay. And this is there's a matching network placed in between, and it is connected to a load that is ZL. In our case, it will be an antenna. So why this matching network is required? You know that there's a famous theorem behind it, that is maximum power transfer theorem. So to ensure, we'll be discussing that in the next slide. So before going that, to maximize the power delivery and minimize the power loss, we need to match this output impedance of the device with the impedance of the antenna or the load impedance. So that's the first point. And also it improves the signal to noise ratio when we talk about sensitive receiver components like LNA and antenna. Also, it reduces the amplitude and phase error as a distributed network such as antenna array. So this is, we are talking about this in a broader perspective. So that's why these all things are coming to picture. Okay. Now let's talk about power transfer theorem. So this is a small signal representation of a simple circuit. This the dotted box. Inside this dotted box is a device which is having a source signal as well as an input impedance represented by RG. Okay, and it is connected to a load resistor which is having an impedance of ZL and resistive value RL. Okay, so here we are explaining three case studies, with three conditions with the load resistance value. So assuming that the source voltage, this source voltage is 10 volt and the source impedance, this one is 50 ohms. So this is the standard industrial standard for radio equipment. This one, only the impedance part. And the voltage we have taken as 10 for calculation. So assume that the load impedance is 30 ohms. Okay, it is lesser than the output impedance of this particular device, less than 50 ohms. Okay, in that case, if we calculate the load power applying Kirchhoff's law, we'll get that the power on the load will be equal to this 0.469 watts. Okay. At the same time, if we increase the load impedance to 70 ohms, now if we calculate the load power, we get it as 0.485 watts. Okay, so this is actually not the maximum power. Now next, when we match this impedance, that is Z load and Z impedance, ZG as 50 ohms, then the power output at the load will be 0.5 watts. So that is the maximum value. So the same thing that is explained theoretically, and the name of theory is maximum power transfer theorem. So this is the proof related to that particular theory. So this is a graphical representation uh, where you can find that the maximum power is delivered when Z load is equal to Z0. Okay, Z0 is nothing but the input impedance. Now the other important parameter is the reflection coefficient. It is represented by this letter. Okay, so it is calculated with this particular formula. We know that when ZL equal to Z0, the value of reflection coefficient becomes 0 when we apply the values in this particular formula. So that means at resonance, the reflection coefficient value will be 0. And there is one more condition for impedance matching, that is the load impedance should not be a short circuit or it cannot be an open circuit. Okay, so it should be some value there. In a real-time application, we cannot use something a radio with coax shorter on the other end, and as well as we cannot open the spear end of our coax without connecting in radio. In that, in both cases, we know that the WR will be maximum. So this is a picture I borrowed from internet. It is a game, it's a reality show in USA, and the void through the hole. The name is the void through the hole. So I just tried to uh, explain the situation, explain the scenario using this image. So if you know that this is a load impedance and this is the input impedance, so you need to make its shape in such a way that you can pass through this void. Okay. So a matching is required there, else we will not able to pass through this void. Now talking about antenna. So we know that even we are using, assuming we are using a normal dipole, that is half-wave dipole, you know that we are just using two wires of quarter wavelength and connecting coax in the middle. So we are, in that case, we are not using any loading coils or any capacitance in there. But when in an AC signal or when an RF signal arrives at the feeder point, it sees this particular antenna. So it sees a inductive reactance, a capacitive reactance, and an ohmic reactance, and a ohmic resistance, and radiation resistance. So these are the different types of uh, elements that an RF sees when it reaches the feeder point of an antenna. So when representing an antenna impedance, it will be a complex impedance which consists of a resistive as well as reactance imaginary part. So what happens at the resonance? So again, during resonance, that is, if you have designed some dipole with a critical frequency, the resonance frequency of 7 megahertz, then at 7 megahertz, the impedance will be minimum. Okay, and the other frequency that is less than 7 megahertz, it will be a capacitive impedance, and the other part the frequencies above the resonance frequency will be an inductive impedance. Now what are the problems which arises when the impedance matching is not met. So whenever the impedance is not matched, and when you transfer a signal to the particular load, then the reflections will occur. Also, a lot of losses will also occur. These reflected waves will reflect back in the transmission line. In our case, it is a coax. So it will come back and forms a standing waves. So this is how the standing waves are formed. And the amplitude of the standing waves will be very high. Like it will be very high voltage that can easily destroy your radio panels. So to measure the standing waves, we have introduced a term VSWR, this voltage standing wave ratio. It defines the ratio between the transmitted and reflected voltage of the standing waves. So this term is very popular, and we all refer this whenever we work on radios before transmitting. We definitely used to check this VSWR. Now, so these all are the issues. So if listen, we know that these all are the problems and occur when there is a mismatch in the impedance. So what is the solution for this? So the solution for this is to place a matched network in between the radio and the antenna. So this matched network we can call it as an antenna tuner. To be precisely, it is just a coupler, and it just matches the impedance and reduces the mismatch between the two elements, radio and the antenna. Definitely, it is just a matching network and it will not tune your antenna. So we don't misunderstand that. If you are making some long wire and say it is not matching the required tuning length, then the antenna tuner will not help to tune the antenna. It will just help to match the impedance with your radio. The antenna tuner sometimes is represented as a coupler. Sometimes it is called as an antenna coupler, transmatch, matchbox, etc. Now let's have a look about of a impedance in various lengthwise of a dipole. Okay, so here I am showing 4 pictures. So this is simple dipole here, that is lambda by 4 length each, and the input is fed at the center of this antenna. Okay, so suppose this particular antenna is designed for 40 meter. Okay, so the total length will be around 21 meters. Okay, so at that time, suppose we are feeding this feeding a 7 megahertz signal into this particular antenna. So this is how the current, voltage, and impedance curves will appear. So this is actually imaginary curve. For just for representation, we are showing it like this. So if you see, the current will be minimum at both the ends, and it will be maximum at the center, and the voltage will be minimum at the center, and the impedance also you can see it is minimum at the center. So we know that for a dipole, the impedance will be around 75, near to 75 ohms. Okay, at the center. So, but we are talking about feeding this antenna on the end of this dipole. So at that place, we can see that impedance is always high. Okay. Similarly, the same antenna, when we feed the second harmonic, that is 7, the second harmonic of 7 megahertz is 14 megahertz. When we feed the 14 megahertz here, this will be the curve. So as you can see, the voltage is at peak at the center, and the current is minimum, voltage is maximum. And also the impedance, you can see that is always on top in the both ends. Similarly, for third harmonics, 21 megahertz, 28 megahertz. So the common you can see is that the impedance is on top on the both ends. Okay. So so we'll be using this this phenomenon for designing the tuner. Now let's talk about the tuner designs. So I'm representing here two types of tuner design that are popular among the ham community. So first one is LMAX, that is L network. So here this is the L network. It looks like an L shape. Okay, and there are two combinations here. If the here it is like if the antenna impedance is less than the radio impedance, then this type of network can be used. Like this type of circuit can be used. And if the impedance of the antenna is greater than the impedance of the radio, then you can choose this type of arrangement. So basically, we'll be using L and C here. And this is a asymmetric circuit, both of these. For a balanced approach and a symmetrical approach, this is another option available of the same L network. Okay. Similarly, uh, this is a T network. So here we use two capacitors and one inductor that is in parallel. It's actually T-shaped. And this one is the balanced T network. There are advantages and disadvantages for all these designs. And next one is pi network. Pi network, we can see that there is a switching capacitor in between. So you need to switch it to move to get a better bandwidth of tuning. Also, in the previous designs like L network and T network, there's a limitation of the bandwidth, that is the range of the tuning. Okay, so it will not help you to tune for a broader range. It will be like a very short range. The T network has a slight better coverage range as compared to the L network. Similarly, in pi network, additional capacitance can be added and switched accordingly as per requirement. So this is a balanced one. And now next is the link coupled. So we'll be discussing more about this link coupled one. So here it is a inductive coupling. So that's why it is called as link coupled. It also provides an isolation. If you see the other type of network, you see that there is no isolation. But in this case, there is an inductive isolation here for the input as well as output. So chances of static and all can be reduced comparatively with respect to the other type of network. And here, the main concern about this type of design is that for QRO application, it will become more costly because of the high voltage rating requirement of this particular capacitor. And the next one is balanced link coupling. Okay, so this is unbalanced one and this is balanced one. Now, next one is a Z match. So this is an effective solution, and many of the commercial tuners are available with Z match. So and next one is S match. This is the latest one, and this is actually described in an ARRL handbook, and it does have some advantages over the previous types of match. So we'll be focusing mainly on link coupling. Our tuner workshop is mainly focused on that type only. So let's discuss about link coupling. Tuner. So link coupling is one of the oldest technologies used for matching antenna and transmitter. It is the simplest method and mostly suitable for like say QRP application. So if you closely monitor, the secondary is a tuned circuit. So we know that the advantages of tuned circuit, it actually acts as a band pass section for the transmit as well as receive signal, and it will also provide a good interference cancellation and boost your required tune frequency. Also, with the help of this type of tuning, we can effectively match a broader range of impedances. And another benefits is like harmonic suppression. And on the transmit and rejects the out of the band signals on the receive. We know that mostly the radio stations are having trouble when they are located near to AM broadcast stations. So you can use this type of tuner setup there. Where you can easily uh, filter out the AM broadcast signals out of the required frequency. Now, building the tuner, it is actually a link. If you see this architecture, like circuit model, you can see that it is a link coupled type of tuner. So I'll be sharing the details about this particular tuner only in this particular session. So here, this is a primary coil, and this is a secondary coil. Okay. And I have wound this on a T52 toroid. It is actually continuous winding with a center tap here. So this portion will act as the primary, and this portion will act as secondary. And the output capacitor, this capacitor in the output circuit is a 2J PVC jam capacitor that is available on old radios for tuning application. It's not meant for high voltage application, but yes, we can use it for QRP for less than say 25 watts. And in addition to this particular, this is a tuning circuit, and here for indicating the SWR. So this is mainly designed for SOTA operation. So that time it will be challenging to carry the SWR meter and all. So to identify the SWR range and just to estimate is it a high SWR or low SWR, we have introduced this particular circuit here. It is nothing but a VSWR bridge. Okay. So it is a bridge and a LED is coupled out that indicates the voltage that is available at this particular point when the RF signal pass through it. So there is a switch, DP/DT switch, as a dual pole, dual throw switch is provided that can bypass the RF signal straight away to the output, as well as whenever we need to measure the SWR, we need to turn the switch on so that this particular SWR bridge gets engaged. It measures the voltage and it will indicate the output in the form of brightness of this particular LED. So brighter the LED, and the higher the SWR, and the brightness is low, that means the SWR is low. So this is about the circuit, and one more point I forgot to discuss here. So in this type of antenna tuners or couplers, the counterpose part is important. So whenever we talk about long wire antenna, the term counterpose is important. It is a debatable point because most of them don't agree about this counterpose. But as per experience from my experimentation, I found that the counterpose is really important. And as per mathematical calculation, theoretically, it should be 0.05 lambda length with respect to the maximum frequency you are using for tuning. Okay. So now this is my prototype here. I'll also show. I have done some modifications on this tuner later, so I will just skip this and just cut this wire and this coax, and I have used this connector. Hope you can see this. So I have removed the cable and I have connected one SO239 compact form factor and easy to carry. The two terminals over here. This will go to the long wire, and this will go to the counter port. Okay. In the front side, we have this knob for tuning the frequency range. It can easily tune from 7 to 21 megahertz. And this is the switch used for switching the SWR bridge and antenna mode. And this is the LED here, if you can see, that will indicate the brightness. So I will share you the making of this. I will straight away demonstrate that. Okay, so this is a video from my YouTube channel where I recorded the entire construction and details and all in testing part also. So please take some time to view this video. I'm playing it straight away. Say 10-minute video, so it will not take much longer.
This is a short demonstration on lightweight QRP tuner for end-fed half-wave wire antennas. I have built this around a small PVC case which is easy to carry anywhere, especially for SOTA operations. It also consists of a small circuitry which will give the SWR indication based on the brightness of the LED, and it can be tunable from 80 to 17 meters. I have only marked for 7 MHz and 14 MHz as per the requirement. So it also consists of two options to switch to SWR bridge and one to bypass the SWR bridge and directly connect to antenna. And it also consists of a tuning knob where we can adjust the tuning frequency from 7 MHz to 14 MHz. On top of the box there consists of two connectors, one for counterpose and one for long wire. On the bottom part the cable assembly is there which is connected to a PL259 connector which will be connected to the radio output. So the back side, the switch I have used is a DP/DT mini switch through which I can connect the SWR bridge as well as bypass the SWR bridge. So these are the components that are required for making this particular tuner. So this is a circuit diagram and these are the assembled part of a few of the components. So this is 200 ohm resistors I have connected in parallel, 3 pair of 50 ohm resistors, and this is the capacitor that I connected in the same resistor, and one small resistor for the LED connection, and also the diode I have soldered in the other end of the resistor. And this is the variable capacitor I am using. It's a 2J PVC type capacitor with range of 0 to 260 picofarad. And this is the tuner coil that I have soldered straight away into the variable capacitor and glued on back side of the variable capacitor using double-sided tape. So the core I have used is T56 toroid. Turning ratio is continuous 3 turns with a center tap and then continuous 26 turns. So this is how it looks. And this is a small PCB housing that I have made for better mechanical strength, and I have already soldered the DP/DT switch on top of it.
I paid ₹99 for your webinar, and if like this 1 lakh people will pay you 99 rupees, then within 3 hours this
and one for taking the connectivity out for the long wire and counterpose terminals. So this is a basic requirement. this is how I make this small housing using the copper clad, and I have soldered a few of the components on it. This is a little bit more progressive completed part with the cable soldered on it. This is almost the final view. I have placed this inside the plastic PVC. Now let's do the testing part of this tuner. I'll be using my scalar network analyzer and the PC for finding the tuning frequency of this particular tuner. I have kept the tuner with the knob marking near the 40 meter. Now let's check using my scalar network analyzer set in return loss bridge measurement. While sweeping from 6 MHz to 9 MHz to get accurate result, I'm getting a steep with SWR as 1.2 near 7 MHz. So it's working. So let's check in real transceiver. This is my Micro BiTX transceiver, and this small switch and wire assembly is the PTT and mic setup of this Micro BiTX. Here are the settings button. On the back side you can see the antenna port. So we'll be connecting this tuner to this particular antenna port. So let's do it. We have to use two wires, one for long wire terminal and one for counterpose. So I'll be using this yellow cable, that is normal electrical 1 mm square wire of around 4 meter length. This will be acting as a counterpose wire. At the same time, I will be using this long electrical wire, that is same 1 mm square, but the length is around 20 meters. So this will act as the long wire of this particular fed half wave antenna. So let's connect it. Connecting the counterpose wire. Now let's start. I have set the frequency at 14 MHz and I have turned on the PTT. Now let's check the tuning. To get the LED indication, we need to turn the switch position to SWR mode. You can see the LED is glowing. We can tune the tuner with the help of this particular knob. And while tuning, we can see that the brightness of the LED is varying, and at some point the brightness is null. This is the same point where the SWR is minimum. So we have to keep the LED at minimum brightness or null brightness to get a better SWR value. So now it's perfectly tuned at 14 MHz. Now for real transmission, we have to change the switch position so that the SWR circuit get bypassed, so that we can use it for normal QSOs. Now let's check same for 40 meter band. So I'm changing the band to 40 meters, that is 7 MHz in CW mode. Putting the tuner in SWR indication mode, I can see the LED is glowing, that means VSWR is high. I'm turning the variable capacitor knob in counterclockwise near the 40 meter marking. Here I can fine tune and I can minimize the SWR to null. So here I can fine tune So you can see the LED is not glowing now. That means the SWR is very minimum. So now the 40 meter is also perfectly tuned. For performing the QSO, again we need to change the switch position so that the SWR circuit get bypassed and it will work as a end-fed antenna. So that's all with this particular video. So this is a simple SOTA antenna which can be easily.
Okay, so hope you guys enjoyed the video. So if you guys got some idea about like how it can be made, and if anyone having any queries or questions or any suggestions, please.
We will start question and answer session. First, identify yourself and fire the question. Please go ahead with Q&A. So first, identify yourself and then ask the question. Over.
Hello, Ravde sir. I'm Makaran Vaidya. Can I start?
Yes, Magaran, please go ahead.
Yeah. My first question is not actually about the core subject antenna, but I saw copper clad enclosure. So I want to ask, what was the purpose of that particular copper clad enclosure? Is that serve some purpose?
Okay, I got your question and thank you for asking. Okay, so actually, I was trying to find a proper case, and I want it should be a metallic case just for a like it will also act as a Faraday's cage. Like it will not the sometimes what happens if we make this thing inside a plastic case, it will start radiating, but it will produce some interference. Or also it can receive the interference from nearby devices like Raspberry Pi and all. It produces a lot of interference, also the LED lights and all. So to prevent that, it is always recommended to build these devices inside a metallic box. So unfortunately, at that size, I was not able to find any metallic box. So I thought I should uh, make one using the copper clad. So copper clad is cheap and easily available, and it can be easily cut into the required shapes and all. So that's the only reason I use the copper clad box here. Hope you got your answer.
Great. Great. The second question about the power supply. You said about the resonant frequency and the first or second slide. Okay. Does that resonant frequency is the cause of noise?
No, resonance frequency is not the cause of noise. Sorry, I didn't get your question. Can you please repeat?
Actually, in the first or second slide, you have shown about the power supplies. Okay. Inductance and capacitance, impedance and all that. Okay. So in that, you said about the resonant frequency, which is caused because of the combination of inductance and capacitance. So is that maybe the cause of any noise?
No, negative. Okay, I got your question. So actually, the first few slides, I was basically explaining about the main terminologies related to antenna theory. So this is actually impedance. Impedance is, I was explaining about impedance. So it will not be the noise, it's just a terminology.
Yeah, it's okay. It's okay. But still, I just came to my mind that can it be a cause for the noise? Because sometimes power supply design is also very concern actually. It's not.
Okay, so actually this is just a term like impedance term. Like if you say the power supply design, yes, power supply, like we talk about the SMPS, that is actually a source of noise. But in standard power supplies, like from a good manufacturer, they
Mhm.
always take care about reducing the EMI, EMF and all.
Yeah.
So there's another step that we need to
Yeah.
take.
Yeah. Just it came to my mind. Thank you. You actually answered my questions very nicely. Thanks for that.
Any any further question? Any more queries?
Yeah, what is the max? This is VU2 Alpha Tango Nancy or Tonu. What is the maximum power this coupler can handle, please?
Okay, thank you for asking this question. It's really great. So actually, as I explained, I used a normal 2 PVC GaN capacitor. That is a PVC, like what do you say? PVC material is used, and it is not an air-type capacitor. So, and the size of the capacitor is very small. The gapping between this capacitor is very minute, like in like micromillimeter, like that range, that type of range. So it cannot handle very high power. So as I mentioned, this is a QRP tuner and can work perfectly below 25 watts. For higher watts, the same design can be used, but the capacitor need to be changed. So at that time, we might need to use air capacitor with high spacing in between, as well as vacuum capacitors also can be used. And also the inductor need to be wound on a better core. So since I am using T52 type toroid, it's a very small. For high power applications, you might need to use air core. So when you move from toroid to air core, we need large number of copper wire, and the diameter of the inductor will also get higher. So it will be a big form factor. So for this prototype, it will work only below 25 watts. Thank you.
Okay, thank you very much.
Atanu is my good old friend right now in Delhi, and very avid home brewer from his beginning of the ham radio career. Thank you, Atanu, for joining today. So any more queries, please? Any more questions?
Yeah, this is
The VK Arya, I think you are also listening. Please shoot out your query.
Yeah, this is VU3 Tango Bravo Romeo from Chennai. Actually, I joined very late when you said 73. That time I joined. But a very quick one to start with. Do you have what I have a VNA, which is small, also easily carryable. And if I add your thing, how it will benefit me between VNA and your, the what functionality does I have not seen. I believe more in believing on seeing and testing it out. Okay, so just give me some feedback on that.
Okay, so I think you're asking about the benefits of having a VNA, like nano VNA. Correct me if I'm wrong.
Yeah, kind of a comparison. I mean, I have a nano VNA, and can I add your gadget also? You made it very clear for taking it outside. It will be small unit, etc. In fact, for my apartment, I use end-fed half-wave with a 5-bander, and many time I check up with the VNA. How your unit is slightly better than or comparative or some points win over the VNA? That's what I want to hear from you.
Okay, got it, sir. Got it, question. Okay, so we cannot compare the VNA with this antenna coupler. But see, this antenna coupler is just for coupling your antenna with the radio and for matching the impedance. And here, a small circuitry is added. That is a simple VSWR bridge is added just to get an indication of what's the VSWR status. That is, like it is very high VSWR, or is it a very low VSWR, or is it a null VSWR? So it cannot be a null point, but you can say that this is a high or it's a low. So if you compare this with a nano VNA in the context of analyzing an antenna, so it will be a very like it is uncomparable, because nano VNA we can get an entire idea like what is the what is the other S parameter details and all. But this is just a simple coupler that will give you the indication, like I said, the VSWR exists or not. So simply that. So you cannot compare that. Nano VN is a pro level, if I say in layman terms. So it cannot be compared. Hope you got my.
Yeah, I agree. I mean, there is no comparison between those. So what I wanted to is, I'll add on this, make something. Another one observation I made is a LED light, which it glows, more resonant, more stronger it becomes, or lighter. So we have to do a guesswork of doing. At the same time, see the knob marking also, how where it is. That's what I could see. But nowadays you get a 3-color, diode base or the LED. So suppose if it is not matching, it becomes red, and green becomes absolutely, yellow. 3-color we can use. This will be much better, I thought. Will it make a, you have to make a lot of changes in your circuitry for doing that? That's one more question I want to ask.
Okay, I'll take this point as a improvement suggestion. Thank you for that. So yes, it can be doable. In that case, I kept this as a minimalistic design. So that's why only a single LED is being used, which is directly connected to an SWR bridge. So it is possible that we can have multiple LEDs, like say the level indication and all. For that, we need to add some additional circuitry, and in that case, such as op-amp or so measuring the reference voltage and then indicate the LED accordingly. For that case, we might need to add an additional external power supply for this device. Currently, this is working without any power supply. It gets the voltage, working voltage from the bridge to the RF signal itself. So in case we need further improvements and all, we might need to add an external power supply for this device. So yes, I will take this input from you.
Actually, rather than having a multiple LED, I was talking about single LED with 3 color it comes. So you don't need a very heavy power for that. With the existing power, you can do that. Nowadays you get a check in the market. I have a digital mode system. It changes the color, blue when listening, when I'm making a cue, so it becomes red. Then green, like that. It's a only single LED, it's not a multi LED. Maybe expensive, but worth it actually, because when you are working you have to be very concentrative, with your existing system. The color will say, it gets mapped in our mind, green means I am okay. Red means sorry, we are offbeat, something like that. We have a mapping of a color. We don't want absolutely 100% accuracy. At least to know what is that coloring can give us some feedback. That's what I said. But there is one LED available with a 3 color. I'll give you some details later. I'll send an email to you, so you can look into that actually.
Okay, copy that, sir.
Thank you very much, Bala. I think we are approaching 9:30 a.m. So I will not be able to take up any more questions. It was a very interesting presentation, Sooraj. We really appreciate your efforts making such kind of a tuner. Of course, we will be conducting very shortly a physical workshop where at least 10 participants will be making this tuner. So thank you very much all for active participation and making this presentation a lively one. We will be meeting next month, first Sunday, for another exciting presentation, technical presentation especially. So I declare the meeting is over, and we will be meeting next month, same time. Have a wonderful day and see you further down the line. Bye-bye.
70s, bye-bye, namaskar.
Namaskar.
So
Thank you.
Yeah,
Thank
Sooraj,
you. Thank you. Thank you.
Thank you.
73 from Bangladesh.
Oh, thank you. Thank you for joining from Bangladesh.
Thank you,
Thank you
Ravadji.
so
Thank
very
you very
much.
much. Thank you, VU2VAV. Thank you.
Thank you. Thank you all.
Okay, Sooraj, thank you. 73. Bala.
Thank you.
Thank you. Bye bye.
73 for Bangladesh.
Oh, thank you. Thank you
73.
from Bangladesh.
Thank you.
Yeah.
Thank you.
Thank